to just talk about this one. So we got a cylindrical drill with a radius of 4 is boring a hole through a center of a sphere with radius 8. Find the volume of the ring-shaped solid that remains. Okay, so here we have the situation, and we're used to having, equations of surfaces and, just telling us to do a double integral. But here it's just a real-world situation, and we have to figure out how to put the mathematics to it. So we notice some key things here. We notice that's a cylindrical drill, and we have a sphere, and we're asked to find the volume. So what kind of thing are we working on right now that enables us to find volume?
Double integral.
Double integrals, right? So double integral, if the function is always positive, right? We've talked a lot about this. If the function always remains positive over the region in question, then the double integral will indeed give us volume. If the surface, whenever it dips below the xy plane, those solids carved out below have a negative contribution to the double integral. So that's why the general way to describe a double integral is by difference of volumes, or net volume, right? All the volume above the xy plane over the region minus all the volume below the xy plane under the region, okay? And so, but if we could set this up so that our surface is always positive, then we know a double integral will truly find us volume. Okay, so we know we've got a sphere, a solid sphere, and we're drilling through with a cylindrical drill. So we want to set this up in R3, right? We want to get this going in R3 so it's like the other problems we've been doing. So if we have a sphere of radius 8, what would be the easiest, most efficient way to model the sphere in R3?
Do you mean like x squared plus y squared plus z squared equals 64?
Yeah, and then, so yes, and that's assuming what? What is that assuming when you do that?
It just adds at the origin?
Yeah, so put the center at the origin, make it the easiest sphere we could come up with, right? So as soon as we start moving away from the origin, that's when the equation gets more complicated. So keep it as simple as possible. Put the center at the origin. Like that. It's the best sphere I've drawn all day. Okay, and so we got radius 8. This. Okay, so now what? So we're going to drill, and if we want to keep things conventional, how do we want to drill the hole through this thing? Which direction should we drill the hole through to keep everything in our most desired conventions?
Through the z-axis.
Right, exactly. So if I drill through the z-axis, then I'll have a cylinder on the z-axis, and then it'll keep my region on the xy plane. And so the cylinder is my cylinder is radius 4, something like this. So we're going to drill through like that, and then all this will be gone then. So all this stuff will be gone. Something like that, drilling through. Okay, so now we got to take this situation and apply what we know about double integrals, right? Double integral, what gives you the volume beneath the surface, down to the xy plane, over the region. So the question is, what's our surface in this problem? What's our region? That's gonna achieve the volume that we want, which is the resulting volume of the sphere after this cylinder is cut out. So, what will our surface be?
Here.
What was that?
The top of the sphere.
Yeah, the top of the sphere, right? So the top of the sphere could be our surface. And then we need to pick the right region so that when we integrate the top of the sphere over the region, we get the solid that they're talking about. So what region do we want? What are we trying to get? We're trying to get this volume like through here, right?
Would the region be radius 4 to 8 and then theta 0 to 2 pi?
Good, right? So the region that we want is like this right here, right? All the way around. So let's draw that in the XY plane. You know, so these are all geometry problems, right? This is a heavily emphasized geometry course. So you're always drawing pictures, right? So there's our hole of radius 4, and then we got the hole of radius 8, or the sphere radius 8. And so if this is the open space, we want the volume beneath the sphere and above this kind of donut or washer shape. So that'll give us the limits of integration. And then when we set up our double integral, just got to get everything right. So our limits of integration correspond to this region and the xy plane over which we're integrating. And then we'll have what a function is the surface. It'll be a function of x and y. And then dA. So we said the sphere was a surface. So how do we get a function of x and y from the sphere?
Would it be the square root of 64 minus x squared minus y squared?
That's right. We're going to solve for z. Okay, or 64 minus x squared plus y squared, like that in parentheses. And then dA, you know, is special. Don't forget how it's special in polar. But we definitely want to do this in polar, right? So, you know, this would be type 1 or type 2. This would be awful, right? This would be really bad. You'd have to split it up. You've got these circle equations which have square roots. So this is very, very well suited to polar. So we're going to change that to polar, our function. We're going to make sure our dA has that special expression in polar. And then we get our limits from this region, and then we can solve the double integral. Any questions? So I'm just going to leave the rest to you.
Professor?
Yeah.
Would we have to multiply by 2? Because would this region just give us the top half of the shape, or is it the full volume?
So what does the double integral give us? It gives us the volume from the surface down to the xy plane. So what do you think? Multiply by 2, or will that do it?
I want to say multiply by 2.
Yeah, all right. Yeah, we're going to need to multiply by 2 to get everything, all of it.
Okay, thank you.
Yep, you're welcome. Other questions? Okay, so I'll leave you to finish that one. And then the rest seem like those who have started working on this, there was pretty high success on the rest of the problems. Please do use if you have questions, feel free to use the email instructor button. Sometimes those emails went through WebWork, go to my spam folder. I try to check my spam folder and tell Gmail that those are not spam, but eventually it kind of happens again. So if I'm not getting back to you within, say, 12 hours, definitely 24 hours on a WebWork email, please reach out to me through direct email and tell me that so that I can remember to check the spam if maybe your message went to my spam folder. So I try to get back within a couple hours, definitely by 12 hours. Try to get back to you on WebWork emails. Okay. Any other questions?
So I approached that problem with the double integral way. I also tried to do it just by calculating the volume of the sphere and then the volume of taken out. And I got the same answer doing it both different ways, and the web work still told me that it was wrong.
Well, so now the volume taken out is a little tricky. So, like, did you include the cap when you did the volume taken out?
Yeah.
So you included this kind of weird part up here?
Well, yeah, because I even did it the integral way, and I got the same answer. So, I don't know. I just...
All right, well, send me your work. Take a picture of your photo. Take a photo of your work and send it to me with all your work, and email it to me. But when you do the subtraction, you know, like you do the whole sphere and subtract. I just didn't know if you included this kind of weird part up here. You'd have to subtract that little spherical cap also. So, okay. But yeah, send me an email with all your work, and I'll look it over. Okay, so we're gonna go on to a very fun topic here, which is triple integrals. So triple integrals. Good stuff. Okay, so triple integral. So here's the deal. With a double integral, let's just review quickly. A double integral what we integrate an R3 surface, right? R3 surface over an R2 region. Okay? So this thing that we're integrating is an R3 surface. It's a surface in R3. And then what we integrate that over is a region in R2. So with a triple integral, it's the same, it's all analogous to that, it's parallel to that, but just everything's stepped up a dimension. So it is, what you have is an R4 surface, which is hard to draw because we live in an R3 world. But it's still an R4, it's like W is a function of X, Y, and Z. So that would live in R4 somehow. And then we're integrating over an R3 solid. So the limits of integration will correspond to a solid in R3. That we can deal with, right? So when we're setting these triple integrals up, the solid in R3 is very attainable, and we can visualize it, imagine it, draw it. Okay, it's just that we just have to kind of, on faith, take this idea that there's kind of what we call a hypersurface in R4, and we're going to integrate it for all the points in R3 in our solid. Okay, so the pictures that we'll draw will definitely be focused on this R3 solid to set up the limits of integration. Okay, so it's the same as a double integral, just everything's stepped up a notch. Double integral, R3 surface integrated over an R2 region. Triple integral, R4 surface integrated over an R3 solid. So here's how we're going to do that. Triple integral. So what we're going to do is we're going to look at the inside integral, and we're going to think about this as surface to surface. We're going to have our archer, and our archer is going to be firing arrows into the solid, and we're going to find out what surface do the arrows go in, and then what surface do the arrows exit. So from surface to surface. And then, here's the beauty of this, then the rest of it is going to be a double integral. It's not going to be step 1, step 2, step 3. It's going to be step 1, surface to surface, and then step 2, double integral. And specifically, the double integral of how our solid projects into a coordinate plane. So this is great. We've been doing double integrals for a week now, and we're starting to get good at those. Many of you are experts, and we're going to use that. So the double integrals that we do are exactly the same as the double integrals we've learned in the last week. Okay, and that's more than half the problem, right? So more than half the problem is doing a double integral. Well, we've already learned that. So there's not a lot that's new here. All right, so here is the first type where we have a solid that's bounded by, focused on a lower surface and an upper surface. So here's the solid we're integrating over, and there's the lower surface and the upper surface. So what will be the first, when we go surface to surface, what will be the first variable that will correspond to this inside integral? Will it be x, y, or z? If there's a lower surface and an upper surface. What's that?
Is it z?
Z, right? So z is going to be first. Here we see that right there. So dz is going to be first. And we're going to think about it going from the bottom surface, the green one, to the top surface, this bluish one. And then, so that's step one, bottom to top surface, and that's in the variable dz, or the variable z. And then the outside double integral will be the projection of the solid into the xy plane. So this gold projection here in the xy plane is what you would get if you like shone a light down on this. It's like the shadow of the solid. Or if you kind of like, as a projectile, you sent it in here and flattened your solid on the xy plane. You get this region in the xy plane, and we're going to do a double integral. It's exactly the way we've done double integrals all along. So that was what we're going to call a type A triple integral. We're going to do z first and go bottom to top, bottom surface to top surface, and then we're going to project that double integral into the xy plane, like flatten it or shine a light and find the shadow of it in the xy plane and do the double integral on that. Okay, for type B. Type B, looking at this picture, what would be our first variable for the inside integral? What variable would we have here? Looking at this.
Will still be z.
Not z.
X.
This would be x, right? So this is showing x, that we're going to have an x, meaning that we're going to go from back surface to front surface. So back to front. And then we're going to take that solid and we're going to project it into which plane?
The YZ plane?
We're going to project it into the YZ plane, that's right. Yeah, we're going to project that solid into the YZ plane. There, you see it back there, the gold projection or shadow of that in the YZ plane. And then we're going to do a double integral in the YZ plane. And we can do type 1, bottom to top, left to right for that double integral, or type 2, left to right, bottom to top, etc. Okay, then the last type, which I call type C, is what's going to be our first variable of integration, the inside integral.
Y.
That'll be y, right? And we'll go from what surface to what surface? From what to what?
Surface to right surface.
Left to right. Left, here's the left, to the right. And then we're going to take that solid and we're going to project it into the XZ plane, this vertical plane over here. And there's the projection right there. And then the outside double integral will be for that region that we get when we send this solid into that plane. Okay, so is this general idea making sense? So what I want to emphasize is that a triple integral doesn't mean like step 1, inside integral, step 2, middle integral, step 3, outside integral. It's actually easier than that in the sense that the only new part to this is figuring out surface to surface for the inside integral, and then getting the right region. And once we have the right region, then we've already done it. It's double integrals. It's a double integral to do that outside. Okay, ready for an example? Any questions on the basic idea? Okay, so here is a tetrahedron. It's a four-sided solid with triangular sides that are planes. And so this is going to be our solid over which we're integrating some function. And what that function is not crucial for our purposes here. So oftentimes solids are called E for solid, and then so there's going to be some function of x, y, and z, and then dv is going to be dy, you know, dy, dx, dz, or dz, dy, dx, or something like that. And so this is just some function that we're not going to worry too much about. What we really want to figure out is how to set up these limits of integration for this particular solid in space. So I have the coordinates of the vertices. 2, 0, 1, 0, 0, 0, 0, 3, 0, and 0, 0, 4. And we got to figure out now that we have 4 planes. So before we get started, you know, trying to write down the limits of integration, let's define the 4 planes. Let's define the 4 planes that we have. So let's start with this, maybe this easiest one here, which is, so my eyes are backwards here. Let's just move this a little bit so we can see how that point 201 is out in front of the screen. Does everyone see that? 201 is coming out at us, right? It's in front of the screen. Sometimes it takes you moving it a little bit to see that. So what about the back plane? There's that right triangle back there. This right here. So how would we write the equation of that plane? What's very special about that plane right there? What plane is that in the back?
The YZ plane?
That's the YZ plane, right? So one of our faces of this tetrahedron is the YZ plane. How do you write the equation of the YZ plane?
You have every variable except for x.
Okay, what is x in the YZ plane?
0.
Yeah. And so it's you have every ordered pair y and z, but x being 0. So that's what defines that plane, x equals 0. All right. So that's one of our 4 planes. All right, another plane is this one here on the left side, right here. What plane is that? How do we write the equation of that one?
Is that ZX?
It's the xz plane, so how do we write its equation mathematically? What's true mathematically?
Y equals 0.
Y equals 0. Okay, so we're 2 down, right? We got the 2 easy ones. The back plane is x equals 0. The left plane is y equals 0. All right, now let's do this bottom one. This bottom plane here, it's kind of angled up. All right, it's
XY.
well, it's not xy because it's right. It's kind of angled up like that, but it does contain the y-axis. Do you see that? It does contain the y-axis, and so because of that, it is special, and we don't have to do a lot of work to figure that out. But just looking right down it, It's this plane right here. So how could we easily write the equation of that plane? This is the point. Now, x is 2, z is 1. This x is...
Z equals 1/2 x.
So z, he wants z equals 1/2 x. What do we think? Z is always 1/2 of x. What about y? Well, y could be anything, right? So this is idea of like a linear cylinder, this plane, where we just have a line in the xz plane, z equals 1/2 x, and then we're going to let it extend in the y direction. So that's plane number 3. We could also write that plane, if we need to, as x equals what? 2z. 2z, right? So those are both equations of that plane. Z equals 1/2 x equals 2z. We might need each of those in different situations. All right, the last one is then this one that's oblique or slanted, angled to all 3 coordinate planes. So there's nothing special, we have no advantage to quickly write this one. So now we got to remember we got 3 points, 2, 0, 1, 0, 0, 4, 0, 3, 0. How do we write the equation of a plane given 3 points? So that was back from the first couple weeks.
Vector.
What's that?
We need the orthogonal vector.
Good. We need a vector orthogonal, right? So let's write the equation of a plane. It's going to be a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. So we need the orthogonal vector, a, b, c. We need any point on the plane, x naught, y naught, z naught. And then we can write the equation down. So how are we going to get the orthogonal vector given 3 points? I think 3 of you all said it. So we need 2 parallel vectors to the plane. Do these points, these coordinates here, count as parallel vectors? No, 2, 0, 1, if you take it as a vector, that's the vector from the origin to that point. That's not parallel to the plane. We need vectors that are truly parallel to the plane. So how do we get those?
Vector from 0, 3, 0 to 2, 0, 1 and to 0, 0, 4.
Right. So we're gonna create vectors from one vertex to another. So how about from 0, 0, 4 to 2, 0, 1, and from 0, 0, 4, it doesn't matter, just any 2 vectors that are parallel. So this vector will be, what, 2, 0, negative 3? And this vector will be 0, 3, negative 4. Now those 2 vectors are parallel to my plane. And how do I get the orthogonal vector given 2 parallel vectors? Cross product. Remember the cross product, you do the determinant of the 3 by 3 where it's ijk, first vector, second vector. The cross product then, the determinant of that matrix gives the cross product, and in this case that'll be the vector orthogonal to that plane. So quickly here, that's like 9 for I, 8 for j, 6 for k. So that's our A, B, C. It's our orthogonal vector that we can put into the equation of the plane. And then which point should we use?
0, 0, 4.
Doesn't matter. Any of them will work. But sure, that's great. Let's do 0, 0, 4. So if I put in 0, and then 0, and then 4, and of course this equals 0, then I'll have the equation of the plane. Plug in 9, 8, and 6 for ABC, my orthogonal vector. Plug in any point, plug in 0, 0, 4. And that's my equation of the plane. Now what we're going to see is we're going to need that equation of the plane in different forms, written as functions of different variables. And the way we do that is we could solve for x, or we could solve for y, or we could solve for z after having this equation. After having those values plugged in, if you solve for x, then you get x, that plane, as x is a function of y and z. If you solve for y, you get that plane as y is a function of x and z. And what we're going to see when we start setting these triple integrals up is we're going to need the different versions of it. Finally, we could solve for z, and then we could get z as a function of x and y. So I'm not going to write all that out. I already have that written down here. Right here. Here's plane number 4, the oblique plane, the more complicated plane. It's number 4. And it has, I've written it as a function, z is a function of x and y is a function of x and z, and x is a function of y and z. So we got the 4 planes. X equals 0, y equals 0, this bottom plane, z equals 1/2 x, and then the oblique plane, which has 3 forms, z equals, y equals, and x equals. Okay, any questions on getting the 4 planes of the tetrahedron? So that we needed all, that was our setup to get ready to start setting up triple integrals now. Any questions?
I'm just confused there. How did we get the -3 and the -4? Are we talking about the parallel? That we picked
So
that parallel.
final minus initial, right? Are you asking about this?
Yeah, definitely.
Final minus initial, right? So the head point minus the tail point to get the vector. Because the vectors give us amount of change, right? How much did x change? How much does y change? How much does z change? You got it?
Definitely.
Okay. Other questions?
Just on the vector.
Cross product, right? Cross product of 2 parallel vectors gives our vector orthogonal to both. So I set up the determinant, and I took the determinant of this, and I got this vector.
So if that would give the resulting vector, the product of the cross product there, why is it we didn't use that one for the initials to find the liking of plane? Rather, we use the 004.
That's the point. There's the orthogonal vector, ABC, and the point on the plane, x naught, y naught, z naught. So yeah, 986, use it right here for orthogonal vector.
Okay. Thank you so much.
Yeah, sure. Sure.
Wait, and then you said that to solve for the z, x, y, and z, do you just from those numbers that you plugged in?
Yeah, you plug them in, and then you just do the algebra. Just do the algebra, solve for, isolate x, isolate y. That's 3 different processes, right? First, isolate x, then come back to this and start again and isolate y. Then come back to this and start again and isolate z, and then this is what you get.
And can you plug in any of the points, or does it?
Yeah,
have to be...
this could be any point on the plane. Yep.
Okay, got it. Thank you.
Yep. Okay, so now we're ready to start writing the triple integrals. So let's do a type A. And what's first when we do type A? So what variable comes first? Z. And so I got my function f. I'm going to do z first. And z is what surface to what surface? If we're going in the z direction first, then we're going to go from what to what?
X.
Bottom to top, right? So the archer will be below in negative z, or just below it, shooting the arrows. And where will the arrows pierce into this thing on the bottom? Which one of the 4 planes?
The XY plane. It's going to the X plane.
No, but the xy plane is not part of our solid, right? The xy plane is not a face of our tetrahedron.
Number 3, Professor?
In the tetrahedron, is the bottom surface raised? I keep forgetting if it is or not.
Yeah, can you see that? So here's the bottom. Can you see that? This is 201 up above the xy plane. Here's the bottom surface.
Oh, okay.
Maybe if I move it around a little bit, that'll help.
X
It's
equals
not.
2.
We never said z equals 0 was one of our surfaces, right? The xy plane is not one of our surfaces. So here, let me move it around.
Would it be z equals 1/2 x?
Yeah, right. So let's move it around here. See? Oh, it's kind of hard to see now with that. Okay. So just to recall what we did. So can you see that the bottom is not the xy plane? The xy plane does not form a face of this tetrahedron. So instead, which of these 4 surfaces is the bottom?
The blue have B and A.
Z equals 1/2 x.
Yeah, number 3. Number 3. That was our z equals 1/2 x. So z is 1/2 x. Okay? And then the arrows are going to enter into that, the 1/2 x down here. And then where are they going to leave? Through which surface are they going to exit out the solid? 1, 2, or 4?
4.
4. So now it's z. So we need the version of plane number 4 that z equals, right? Z equals what? Here it is. The top one, the first one. Negative 3/2 x minus 4/3 y plus 4. So we enter in z equals 1/2 x. That's the bottom surface. The top surface is that last complicated plane we found. And since it's z equals, we need the version where z equals a function of x and y. Okay, so now we got bottom surface to top surface, and we're going to now project this thing into which plane?
The XY plane.
We're going to project our solid into the xy plane, figure out what region we get, and do the double integral for that region. So think about how this thing projects. So we can look at these, you can project points to see how the whole thing projects. So that will project here to x equals 2. That'll just be 0, 0. That'll be 0, 3. And so then this blue line will just project as a line connecting those two. So something like that. Let's draw it down here. So we got the point x equals 2 there, and the point y equals 3. And then it's just going to be, and then the x-axis and the y-axis. So that's our projecting region, and I can let's see that from above. So I can grab the solid here and look straight down. So looking straight down in the xy plane, you see the same thing that I drew over in the bottom right corner. Right? So this is 2. That's that point 210, 201. Here's the point 003. And here's the solid. You're looking right through the solid into the projection in the xy plane right there. So it's this here. Does that make sense?
How did you get your upper z bound? I think I missed that.
This one here? You're talking about
yes.
So we go surface to surface. We go bottom to top, right? Bottom surface to top surface. So the arrows come in through this surface. They exit out the oblique plane, the last one, the complicated one. Do you understand that?
Okay, yeah.
That was plane number 4. So since it's z, we need the version that z is a function of x and y. We need this version here.
Oh, I got you. Thank you.
Yep. Okay, so now we're just going to do the double integral on this right here, where this is x and y. And so let's do type 1, which is dy dx. So we'll do dz, dy, dx. And then, so y, that means bottom to top. And then left to right. Those strips left to right. So what's the bottom of this thing? dy first. Bottom is?
0.
0.
2, 2, 3.
This is y equals, what, 3 minus 3/2 x. This top here, right? So that's that line. Y-intercept 3, slope negative 3/2. So we're going to go from 0 to 3 minus 3/2 x, just like all the double integrals we've been doing. And then finally, from left to right, the leftmost strip is at x equals 0. The rightmost strip is at x equals 2. Got it. So there's our outside double integral, which is just the double integral on that region, which we projected into the xy plane. Okay, questions on this? So this would be like type A1, right? Type A1 would be dz, dy, dx.
Professor?
Mm-hmm.
So when we did double integrals, it gave the sign volume. Does this also have a geometric meaning?
Yeah, so it's like signed hypervolume. So because it's tough because the function is an R4. So whenever this function is negative, you get like this analogy of like a hypersolid that's kind of what? In negative W territory, right? And so then that will get subtracted out from this. And whenever this is positive, it'll have a positive contribution to this. But the thing, it's like difference of 4-dimensional volumes, basically. It's the difference or the net 4-dimensional volume.
How do we interpret these 4-dimensional volumes?
Don't worry about it. You're not responsible for that.
Then what's the purpose of learning this?
Well, there's applications. Like this could be like a density function, so like rate of change. This could be density. And so say the density is continually changing throughout this. So as density is rate of change, so like, milligrams per centimeter cubed or something. And then if you did a triple integral and you integrated that, then you would be finding out what the total mass is of the whole thing with a variable density. But there's lots of other applications too. It's not just that. But that would be one application. Okay, so should we do another one here? Oh, and by the way, so there's no in-class quiz today, so we still have 5 minutes left to work on this without stress. Don't be stressed out. There's no in-class quiz. So let's do. I want to do so type A2. Let's just talk through it. It'd be the exact same surface to surface, bottom to top surface. This would be the same, and then you would just do the type 2 double integral, which would be another easy one, right? You'd start with left to right. And then you'd have this first strip at the bottom and all the strips up to 3. So I'm not going to do type A2. I think you can do it. You guys are experts at type 2 double integrals. It would just be this thing, dx dy, right? Type 2. And then that would be your limits for this outside double integral. So I'm going to go to type C. I want to look at type C right now. Do you remember what we said type C was? And not that you had to memorize the names of the types. It just helps us to give, you know, a common name to them. But what did we say type C was?
Is it left to right?
Yeah, left to right first. So what variable comes first?
Or Y?
Y comes first, okay? So we're going to do F dy first, and that's left to right. So then our archer is going to stand over here and fire the arrows into this side over here. And where are those arrows going to pierce into the solid? Surface 1, 2, 3, or 4?
1.
Okay, I have a vote for number 1. Coming from the left, what was this plane again over here? That was number 2. That was y equals 0, right? Yeah, so it's going to be y equals 0. And then where are those arrows going to exit? So we got one that comes in here, right? Boom. And then it's going to exit out. Which plane do the arrows exit out of?
From 4.
Number 4 again, right? So before, the 4 was the top, but now it also serves kind of as the right, right? So those arrows are going to go into y equals 0, and they're going to exit out of this, again, this front oblique plane. But now it's in terms of y, right? We need y as a function of x and z. So we're going to use this version. So negative 9/8. So same plane, but now it's, what is y equal to? Y is equal to this. So enter in y equals 0. I want that erase. Come on. All right, so we're going to enter in. Let's move it a little bit. I think it helps once you start moving it to see what's going on. So we're going to enter in y equals 0. That's the xz plane right there. And then it's going to enter in there. It's going to exit out this plane. Everyone see that? So enters plane number 2 that we labeled number 2, exits plane number 4. Okay, and now we're going to project this solid into which plane?
XZ.
We're going to project it into the XZ plane, and we're going to do the double integral of the resulting region that we get when we project it into XZ. So this point is in the XZ plane already, and that's 2, 1. And this point is up here, is already in the XZ plane. Is that 4? And then so we see that from 0, 0 out to 2, 1 and to 4, so it's going to look like this. And let's take a look at that to make sure. So I'm going to come over here and take a look down the y-axis at the XZ plane. And we will see exactly what I drew. Does that make sense? See that? So there's the projection of this thing into the XZ plane. And so now we're going to go bottom to top. So if we do a type 1 again, type 1 will be bottom to top. What's the bottom? Yep, so it's going to be what? So this is, we're going to do Z first, right? So DZ, bottom to top is DZ, and then DX. So Z equals what? Z equals?
1/2 x.
1/2 x. Z equals 1/2 x. That's the bottom. And the top is, so this is going to be Z equals y-intercept, or Z-intercept 4 minus, what is this? We're going to go down 3 minus 3 halves x, I think. Yeah, so down 3 for over 2. If you plug 2 in, For x, you get 1. So it works. So we're going to go from 1/2 x to this line from the point 0, 4 to 2, 1, which is this line here. So that's 4 minus 3/2 x. And then those starting which strip? What's our first strip on the left? X equals?
0.
0. And our last strip on the right?
2.
2. So here's type C1, meaning y first and then our type 1 double integral. What would happen if we did type C2? What would happen with C2? Do you see that the right side of the region is broken up? So that would force us to split this triple integral apart. We'd have the same inside single integral for the surfaces, left to right. But then when we get to the outside, we have, for our boundary, our right boundary of this region, split up. So that would force us to, just like we split up double integrals before, we're going to split up the triple integral because the double integral, we have 2 double integrals because of the broken up right side of this region.